Hello everyone. Today I will talk about Epsilon Delta Proof. The objectives are first I will talk about what is the Epsilon Delta Proof, and then I will explain the procedure and how to use this method to perform a mathematical proof. And I will give you two examples and then do a summary. Okay, let's start. So suppose there's a function y equal fx is a continuous function for one variable, and also f x sub 0 equal l, which l is a constant. So the definition of epsilon delta proof is a mathematical description. So let's look at this picture, the right side picture. And when we see when x equal to x sub 0, then the f x will approach to some value here, for example, L. We can use the following description, which means for a given neighborhood of capital U of L, then there is a neighborhood of capital V of x sub 0, such that whenever x in the domain V, which is blue area, then fx will be in the domain or the region U, which is the red area. So in mathematics, it requires the specification. So how can we specify the above statement? So we can rephrase the above description by using epsilon delta. Okay, so that is for a given positive epsilon, there exists a positive delta such that whenever the absolute value for x minus x sub 0 less than delta, then the absolute value for fx minus L less than epsilon. So this is the fundamental of epsilon delta proof. And also, when you learn calculus, you will learn the concept of limit. So the epsilon delta proof also is said that it is a technical definition for limit. So let me explain it. So the definition of limit is like this. For example, here the interval capital I is an open interval contained number c, and let f be a function defined on the interval I, except the possible at c, which is then the statement that the limit of fx is L when x approaches to c is denoted by LIM, usually called limit fx equal L when x approaches to c. So this definition can be described by epsilon delta proof, which the definition can be rephrased by that for giving any positive epsilon, there exists a positive delta such that for all x in interval I, if the absolute value of x minus c less than delta, then the absolute value of fx minus L less than epsilon. So in other words, when there's a forgiving positive epsilon, there always exists a positive delta. Whenever the x approach to c or close to c from both sides, the bigger side or smaller side, that's why I use the absolute. When x approach to c, then the fx will approach to L. That is the technical definition for limit. Let me explain the procedure and how to use this technique to prove mathematical or a limit or other mathematical problem. So the fundamental statement is for giving any positive epsilon, there always exists a positive delta, such that for all x in a domain, for example, domain R, if the absolute value of x minus x sub 0 less than delta, then the absolute value of fx minus L less than epsilon. So the procedure is as follows. First step, for giving positive epsilon, you assume or you let the absolute value of fx minus L less than epsilon. That's the first step. Second step, take advantage of the absolute value of fx minus L less than epsilon. Simplify this inequality into the form absolute value of x minus x sub 0 less than c multiply epsilon, where c is a positive constant. The final step, you just define the delta equal to c multiplies epsilon. Then you complete the proof. Why? The reason is the mathematical logic in step 2 is invertible, which means for a given positive epsilon, you already found a positive delta. So whenever the absolute value of x minus x sub 0 less than delta, then the absolute value of fx minus L less than epsilon, which is this statement is satisfied. Let me use the example to demonstrate how to use this technique. So the first example is the proof that the limit of fx equal to 2 when x approaches to 1, where fx equal to 3 multiply x minus 1. So first step, for giving positive epsilon, we suppose the absolute value of fx minus 2 less than epsilon, such that the absolute value of 3 multiply x minus 1 minus 2 less than epsilon. Then this inequality can be simplified as the following, which is the absolute value of x minus 1 less than epsilon divided by 3. So final step, we define delta equal to epsilon divided by 3. Therefore, for all positive epsilon, we found there is a delta equal to epsilon divided by 3, also positive. And if the absolute value for x minus 1 less than delta, then the absolute value for fx minus 2 less than epsilon, such that the limit of function fx equal to 2 when x approaches to 1. Simple, right? Okay, let me show you the second example. So prove that the limit of fx is equal to 4 when x approaches to 2, where fx is equal to x squared plus x minus 2 and x in the domain in the interval 1 to 3. Okay, so first step, for giving positive epsilon, we assume the absolute value for fx minus 4 less than epsilon, such that the absolute value for x squared plus x minus 2 minus 4 less than epsilon. So the inequality 1 can be simplified as the absolute value for x squared plus x minus 6 less than epsilon. So since the quadratic form x squared plus x minus 6 can be factored as x minus 2 multiply x plus 3. So the inequality 2 is equivalent to the following, which is the left side hand can be represented by the 2 factor, which is the absolute value of x minus 2 multiply x plus 3 equal to the absolute value of x minus 2 multiply the absolute value of x plus 3 less than epsilon. So if we divide x absolute value of x plus 3 two sides, then we got the inequality 3. That is the absolute value of x minus 2 less than epsilon divided by the absolute value of x plus 3. So for the left hand, is okay. That's what we want, which is the absolute value of x minus 2. For the right hand, there is a variable, which is the absolute value of x plus 3. So we want a constant, not a variable. So we need to get rid of the x in the right hand. So here we apply the given condition, which x is in the interval 1, 3, such that x plus 3 bigger or equal to 4 and less than or equal to 6. So we know for two positive numbers a and b, if a less than or equal to b, then the reciprocal of a bigger than or equal to the reciprocal of b. We apply this property, then the inequality 4 is identical to the following inequality, which means 1 divided by 6 less than or equal to 1 divided by x plus 3 and less than or equal to 1 divided by 4. So if we apply the inequality 5 to the inequality 3, we will get the following, which means that the absolute value of x minus 2 less than epsilon divided by absolute value of x plus 3 and less than or equal to epsilon divided by 4. So here, be careful here, and there's the absolute value of x plus 3, and but the inequality here 5, there's no absolute value, but because this absolute value for x plus 3 is the same thing, because x plus 3 always positive from this inequality 4, right? Bigger than 4. So then we use the final step, we define delta equal to epsilon divided by 4. So therefore, for all positive epsilon, there exists the delta equal to epsilon divided by 4, also positive. If the absolute value of x minus 2 less than delta, then the absolute value of fx minus 4 less than epsilon. So therefore, we prove the limit of function x is 4 when x approaches to 2. Simple, right? So let me do a summary. So suppose you need to prove that the function fx, the limit is L when x approaches to x sub 0. So first step, you just give suppose a positive epsilon and let the absolute value of fx minus L less than epsilon. Second step, take advantage of the inequality and simplify the inequality into the form absolute value of x minus x sub 0 less than c multiply epsilon, where c is a positive constant. Then final step, you define delta equal to c epsilon. Then you complete the proof. So let me give you a homework. Please prove that the function fx, the limit, is equal to 3 when x approaches to 1, where fx is equal to 2x plus 1, 2 multiply x plus 1. Thank you for watching. If you like the video, please give a thumb up or subscribe to my channel. I will release more videos. Thank you.